Swayam Prabha. Digital India. Educated India.
Hello everyone. Today we are going to start the 6th week of this course, and in this week our focus will be finite element formulation for plane crosses and frames, and also particular emphasis on computer implementation. And today, the first lecture of this week, will talk about element formulation. You see, we are almost halfway through of this course, and if you recall at the very beginning, we mentioned there are two aspects of this course. One aspect is understanding the theoretical formulation, and then another aspect is the implementation. In the last 4 weeks, we had a discussion on the basics of finite element methods, some theoretical aspects in the context of few boundary value problems. For example, bar problem and then beam problem, Timoshenko beam problem, Euler-Bernoulli beam problem. Now what we'll do in this week is we'll take a pause and then see and start discussion on the implementation aspects. Whatever we have learned, that understanding is sufficient to analyze a truss and frame problem. So based on our understanding, based on the discussion in the last 4 weeks, we will try to analyze the truss and frame problem, plane frame and plane truss and plane frame problem. So in this week what we will do is the application of finite element to plane truss and frame problems. We will do 1 or 2 examples manually just to understand or just to comprehend the steps involved in finite element method. But then once we have a large scale problem, this manual calculation is not feasible. Then we will see if it is to be implemented in a computer code, how it is to be done. And then once our computer code is ready for solving large scale problem, we'll also talk about the convergence and some concept of error. If you remember, in the very first week we had discussed the concept of convergence and error in the context of 2 problems. One is the determination of circumference of a circle and determination of area of an arbitrary shape. Here towards the end of this week we'll also discuss what it means, the convergence and error mean in the context of finite element method. Now just to first review the basic steps involved in finite element method, we had discussed it several times, but it is important to keep that in mind before we start implementing it. We have a boundary value problem, and then discretization of the domain. Discretization of the domain means discretization of the domain into elements, and then derivation of element equation. Assembly of once the element equations are written, then we need to assemble those equations to get the global equations, and this assembling has to be done based on the element connectivity, how the elements are connected with each other. Then once we have the global equation, then imposition of boundary conditions, and then final solution, and then of course postpositioning. Once we have the solution, how to visualize the solution, how to extract the other information from the analysis. Now where do we stand now? Boundary value problem, at least bar problem and the beam problem already discussed. And discretization of the domain is also discussed, and derivation of the element equations for bar element and for beam element already been done. Assembling of element equations, some discussion probably we had, but then in this week we will have detailed discussion on this, how to assemble them based on the element connectivity, and then imposition of boundary conditions, and then finally solution. So these are the steps. Every steps we will be we will be working on, and we will try to understand all these steps through some example. Okay, so this is quickly the review of the summary of the discussion in last 4 weeks. So you see, if you have a bar problem, 1D bar problem, and then this is the building block, the elements are the building block, right? We know that, and this is the 1D bar element. We have 2 nodes here, and at every node we have 1 degrees of freedom, and therefore for the entire element, we have 2 degrees of freedom. The element equations are written like this, and the stiffness matrix is a 2 by 2 matrix because we have 2 degrees of freedom, U1 and U2, and these are the generalized forces. Now, these equations are written with respect to element coordinate or the local coordinate, and then in actual structure we have a coordinate, say x, y. These coordinates are the global coordinate. But in this problem, at least the orientation, if you see the local coordinate, the element coordinate and the global coordinate, their orientation same. Therefore, the element equation will remain unchanged. This is for 1D bar problem. And then we also discussed Euler-Bernoulli beam problem. This is the building block, and then we have 2 noded beam element here. For at every node we have 2 degrees of freedom. One is translation, transverse direction, and another is the rotation. So stiffness matrix will be 4 by 4 stiffness matrix. The equation is this, where this Fe part is the contribution from if you have some distributed forces, and which Fe can be obtained from this. Fi are the shape functions. We know the properties of shape functions, various properties of shape functions, and then Qi are the if you have some concentrated moment or the force, then these are the Qis, and it also includes the support reactions. And this is the, and if we see the stiffness matrix, if we partition the stiffness matrix like this, then this block correspond to node number 1, this block corresponds to node number 2, this is for node number 1, and this is for node number 2. Now, if we look at this stiffness matrix and the stiffness matrix for bar element we had seen in the last slide, you have already seen these stiffness matrices, not just in this course, even much before that, when you had the matrix method of structural analysis or direct stiffness method. There you had seen these stiffness matrices. But then the approach to the procedures that we adapted to derive the stiffness matrix in finite element method, and the procedures we had adapted in deriving this stiffness matrix in matrix method of structural analysis or direct stiffness methods, both are different. Okay, these approach what we had discussed in previous weeks in finite element method, this is a more general approach. Okay, it comes directly from the governing equations of the problem. So this we discussed. Now we have to, since our objective is to solve finally plane truss and plane frame problem, let us see the bar element and the beam element that we have seen, how it can be adapted in plane truss and plane frame problem. Let us start with truss. So this is a truss problem, and this is the bar element. Now you see, this is the local coordinate, and you have a global coordinate something like this. This is x and this is y, right? You see, so this is the stiffness matrix. Now next is let us, it is the same. This element, this element and this element is, these 2 elements are essentially same, but written, these elements are, this is written in a slightly general form. You see, in a bar problem, yes, deformation is axial. Now we have, in addition to these axial deformation, these U1 and U2, these 2 degrees of freedom, we had also taken these 2 degrees of freedom, and Q1, Q2, Q4, Q3, Q4 are the forces associated corresponding to those degrees of freedom. Now if we take these as our element, as the building block, then the stiffness matrix, these stiffness matrix can be written in this form. These 2 essentially are same. You see, because the deformation is in only axial direction, there is no deformation in this direction. That's what our assumption in for a truss problem. So that's why the corresponding entities are 0. So essentially, if you write these equations, and this equation gives you gives you this stiffness matrix only. Okay. Now, this is written with respect to the local coordinate system. This is the local coordinate system. But now, you see, in a class we have several members connected with each other, and every member, the orientations are different. So when we add the forces, when we apply the equilibrium conditions or compatibility conditions, everything, equations are to be written, or these variables need to be determined or need to be represented with respect to a fixed coordinate system for all the member. Okay, so now this is the same frame, same bar element, same cross element, but now the degrees of freedom and the forces are expressed with respect to the global coordinate system, x, y, global coordinate system. Okay. And now our job is to, we already know what is the stiffness matrix for this element with respect to local coordinate system. Now our job is to find out the stiffness matrix with respect to the global coordinate system. This transformation needs to be discussed, and this is called this transformation, TE, is called transformation matrix. We will derive the transformation matrix, and this transformation matrix transfer these equations which is written in element coordinate system or local coordinate system to the global coordinate system. We will discuss that shortly. Similarly, for a frame problem, you have this is the element, your building block of the frame. Now, at every point you have 3 degrees of freedom, 2 translation and 1 rotation, and these degrees of freedom and the forces are expressed with respect to the local coordinate system. What we will do, we already know the elements for bar element. We already know bar elements and the equations. We also know the beam element and the associated equations. What we will do, we will combine these two to determine, to see or to write the equations for a frame element. Now, if this is the building block, this is the element required for analyzing a frame, then this element can be decomposed in 2 parts. One is this and another one is this. You see, these 2 parts, one is only, which the first part only takes care of the axial, the deformation in axial direction. The degrees of freedom in the axial direction means U4, U1 and the corresponding forces Q1 and Q4. And the second part is the transverse. Transverse I am saying with respect to the local coordinate system. So if this is your local coordinate system, so this direction is the transverse direction. So this element is the transverse direction displacement and the forces, and the rotation. Rotation, corresponding displacement, corresponding degrees of freedom and the forces. So this is if you look at, this is essentially 1D bar and this is a beam, and for both the cases, for 1D bar and for the beam, both the cases we already know what are the stiffness matrices and what are the equations, right? So for bar element, what is the stiffness matrix? This is the stiffness matrix, and this stiffness matrix is for what are the degrees of freedom. This is for degrees of freedom 1 and 4, because we have 1 at one end, one node, and 4 at another end. So this is the stiffness matrix for bar, and this is the stiffness matrix for beam element. And these, what are the stiffness matrix? What are the corresponding degrees of freedom? Corresponding degrees of freedom are U2, U3, U5 and U6. U2, U3, U5 and U6. U2, U3, U5 and U6. Now what we will do, now we will combine these two, the stiffness matrix for bar and the stiffness matrix for beam. We will combine these two to write the stiffness matrix for this element which we need to analyze a frame. And if we combine these two, then this becomes this. Now this is written in terms of their degrees of freedom. So you see here 1 1 is 1. So 1 1 is 1 means 1 1 is AE by L. So 1 1 is 1 1 is mu, and mu is written because of you have taken this as in common. So you can find out what is the mu. Then you write 2, 2 is 6 with this portion as common. So 2, 2 is 6, and then say 2, 5 is minus 6, 2, 5 is minus 6. Let's take 6, 6 is 6, 6 is 2L square, 6 is 2L square. So this is the stiffness matrix for this element, for the frame element. But please note, this stiffness matrix written in terms of the local coordinate system. Okay. Now, so this stiffness matrix now read to be, this is the same beam in same frame element, but now degrees of freedom and the forces are represented with respect to the global coordinate system, and this transformation we have to do from local coordinate system or element coordinate system to the global coordinate system. So this is the comparison of truss and frame element. If you look at this truss and frame element, only difference is you do not have these degrees of freedom, this rotation at the end in case of truss element. So these degrees of freedom are not there. Okay. So in that case, we can see that the truss is essentially a special case of frame when we remove these degrees of freedom. So what we do, once we know that the frame truss is a special case of frame, let us find out the transformation for a frame problem, for a frame element, from local to global stiffness matrix, and then from there we will find out what will be the equations for truss. Okay. So transformation from local coordinate to global coordinate. You see, now this is your local coordinate system and corresponding degrees of freedom and the forces. This is global coordinate system and the corresponding degrees and the forces, degrees of freedom and the forces. This is the equation with respect to local coordinate system, and this is with respect to global coordinate system. Please note, when we say the transformation, it is not transformation, it is not only the transformation of the stiffness matrix, it is transformation of the entire equations, and that equations involve your degrees of freedom and force and the stiffness. All needs to be transferred. So let us do that exercise. So let's take this coordinate system, x, y coordinate system, which is, as per our notation, this is the global coordinate system, and then we have prime coordinate system x bar and y bar. This is local coordinate system or element coordinate system, and suppose this angle between these two coordinate system is alpha. Okay, and this alpha will be different for different members. If you are solving a truss problem, a frame problem, you take different members, different elements, the orientation of different elements will be different, and therefore alpha will be different. So we will write the equation in terms of alpha, and when we implement it, we know what is the alpha for a given element, and we substitute alpha to get the equation for that particular element. So we know that if x and x bar, if we have to transfer any coordinate, this is the coordinate, this is the transformation. We know that. Okay, this is the transformation from. So if you know x bar, y bar, this is how we. If you know x and y, this is how we can calculate x bar and y bar. Now take this element. Now you see, similar to x and y, this element has, at every node we have 3 degrees of freedom, and 2 are translation, these 2 are translation, and this is rotation. These 2 are translation and this is rotation. Now this translation degrees of freedom means at node number 1 u1 and u2, and node number 2 u5 and u6, they can be translated same way as x, y, right? So if we have this is the global coordinate system. So u1, u2, u1 prime and u2 prime, and u1 and u2, they are related to each other in the same way how x bar, y bar, and x, y are related to each other, and same thing goes for u5 and u6 here, and u5 and u6 here. But okay, this is for the translation degrees of freedom. What happens to the rotation means the degrees of freedom u6 is the degrees of freedom. So U4 and U5 are the translation degrees of freedom. What happens to U3 and U6? You see, because of this transformation, U3 and U6 will remain unchanged. So whatever angle you have with respect to this, the same will be there, the same rotation will be there with respect to the global coordinate system. So we can say that U3 prime equal to will be U3, and then U6 prime will be equal to U6. Now with this information, we can write this transformation of degrees of freedom at node number 1 like this. So these two, U1 and U2, U1 and U2 are will be transferred the same way as X and Y, and U3 will remain unchanged, and the same thing can be written for other degrees of freedom at the other node, means U4, U5 and U6 the same. So this is at every node degrees of freedom are transferred, transformation of the degrees of freedom done like this. Now what we'll do now is we will combine these two individual transformation, and if we combine this can be written as this, you see. So here all these degrees of freedom with respect to local coordinate system, and here we have degrees of freedom with respect to global coordinate system, and these are the transformation matrix. Okay. Now this is, so this can be written as, now this is equal to this, and this TE is called transformation matrix. There is an interesting property of this transformation matrix. I'm sure that you are aware of this. You have learned this in matrix method of structural analysis, in solid mechanics as well. This transformation matrix is orthogonal matrix, means this transformation at this transpose of this matrix is essentially the inverse of the matrix. Okay, that is an interesting property. This property will help us, or we'll see, because of this property our final equations will be relatively simpler. So this is how we have the transformation of the degrees of freedom. Okay. Now similarly, the way we have transferred degrees of freedom, similarly the force vectors can also be transferred from prime coordinate system to your local coordinate system to global coordinate system. Okay. Now next is, so let us see what we have now. We have seen that this is how these degrees of freedom are transferred. This is how the force vectors is transformed, and this is the property of the stiffness matrix. Now this is the element level equation. K bar, U bar and Fe bar, these are the representation of stiffness matrix, displacement, degrees of freedom and the force vector with respect to local coordinate system, the prime coordinate system. Now with this information, if we substitute this in this equation, what we have is, now we have this, if you substitute U bar from this, we have this, and then Fe bar from this expression, we have this. Now if you multiply both sides by inverse of transformation matrix, we have this. So this becomes Fe and this is your this. Now we apply the property of orthogonality. This matrix is orthogonal. So inverse of this matrix is essentially the transpose of this matrix. So we have this transpose of the matrix, right? Now look at this. This was the local equation, element equation. Now we have equation, this part, if we take, and this is some measure of stiffness, and this is force written in global coordinate system, so displacement written in global coordinate system and force written in global coordinate system. This becomes KE. KE is equal to, KE is the stiffness with respect to global coordinate system, which is essentially equal to this TE transpose K bar TE. T is the transformation matrix. So similarly, we already have seen this. So these two equations are now important for us. So we already know what are the element level equation, and then these two equations will tell us how this element level equation can be, how with this element level equation the global equations can be formed. Okay, so let us summarize what we have discussed now. This is for a frame problem. For a frame problem, this is the transformation matrix, and these are the summary of the equation, and this is the stiffness matrix, and this angle is alpha. Okay. Now from the frame problem and these blocks, this portion is corresponding to node number 1, this portion is corresponding to node number, these interaction between node number 1 and 2. This is how we can read these matrices. Now, so this is the summary for a frame problem. Now from there, if we have to determine the similar thing for a truss problem, what we can do? Only difference between the truss and frame is we do not have the third degrees of freedom, the rotation degrees of freedom. So we do not have U3 and U6 we do not have for a truss problem. So if we remove these corresponding rows and corresponding columns, if we remove these corresponding rows and column, we will get the transformation for a truss problem. So for a truss problem, your transformation will be this, and this element stiffness matrix we have already seen. This element stiffness matrix is this, and these are the equations for global. These are the global equations. Okay. Now, where we are now? Now we know, based on the, let us now summarize what we have discussed so far once again. So we know what is the stiffness, what is the equations for a bar problem. We know what are the equations elements for a beam problem. Now with this information we find out what is the equations, what are the elements for a frame which is required to analyze a frame problem, and then what are the equations to analyze a truss problem. So all these equations for frame and truss we have with us, right? Next, what we'll do is we'll take one example, and then relatively simpler example, maybe with maybe say 2 members or 3 members in the structure, and then we'll try to analyze. Whatever equations we have so far, we'll use them to find out the solution of that problem manually. We'll implement all these steps manually just to understand those steps, just for a better comprehension of those steps. Now once we have done this, next, same thing what we manually calculate, the exercise we do manually, same exercise we will do through a computer code. We will write that computer code, we will see different aspects of this computer code, and then solve a large problem with more elements and more degrees of freedom. And once we will be in a position to do that, we will discuss the convergence and error in finite element analysis. So with this, let us stop here today. See you in the next class. Thank you.